Welcome you all in the lecture number 24 of Abstract Algebra MTL 6051. In this lecture we will going to discuss fundamental theorem of ring. Right. Second fundamental theorem. And third fundamental theorem. Okay. Example related to this, related to the fundamental theorem, and construction of factor group. Construction of factor group. Okay. See the fundamental theorem of ring isomorphism. Okay. If F from R to R prime be an onto homomorphism, then R prime is isomorphic to quotient ring of R, right? R plus dot, R prime plus and dot be two ring, okay? And F from R to R prime is onto homomorphism, okay? Onto homomorphism. Then R to R prime is onto homomorphism. Then this R prime is isomorphic to R by kernel of F. Okay. Now see R to R prime. This is F. Okay. This is F. Then from R to R by kernel of F. Kernel of F. This is natural homomorphism pi. This one is not phi. This is pi. And R by kernel of F to R prime. Say this is phi. Say this is phi. Okay. Now this phi is defined as any element of this. What is the element of R by kernel of F? That is X plus kernel of F. Okay. X plus kernel of F is what? Phi of X plus kernel of F is element of R prime. Say this is F of X. Since F is a map from R to R prime. Okay. So this phi is defined in this way. Now, to sort our notation, we will assume kernel of phi is I. What is kernel of F? What is kernel of F is? Kernel of F is I. And what is kernel of F? This is an ideal. This is an ideal of ring R. Okay, ring R. So we will define phi from R by kernel of F to R prime, and we will prove it. This phi is 1 onto homomorphism. Okay, 1 onto and homomorphism. That is, this phi is isomorphism from here to here. Then R prime is isomorphic to R by kernel of F. If we are able to show that this phi is 1 onto and homomorphism. So this phi is defined as phi of X plus kernel of F. What is I? I is kernel of F. Phi of X plus kernel of F is Fx for all X belong to R. First we will show that this phi is well-defined map. Okay. This phi is well-defined. If any two elements are equal, then their images are equal. See, X plus I is equal to I plus I. X plus I is equal to I plus I. Then X minus Y belong to kernel of F. X plus I is equal to I plus I. Then X minus Y belong to I. I means kernel of F. If X minus Y belong to kernel of F, then what is Fx minus Y? If this belong to this one, then F of X minus Y is equal to identity of E prime. Okay. Right. Then what is this? This is Fx equal to E prime plus Fy. What is E prime plus Fy? That is Fy. It means Fx is equal to Fy. Fx equal to Fy means what? What is Fx? Fx is phi of x plus I. And what is y? Fy. Fy is phi of y plus I. Okay. It means if the elements are equal, then their images are equal. So phi is well-defined map. Okay. Next. This phi is onto. Sorry, this phi is homomorphism. Right? This phi is homomorphism. If phi is homomorphism, then what is the definition of homomorphism? Phi of x plus y is equal to phi of x, phi of y. Something this type of definition. But what is phi? Phi is a map from R by kernel of f to R prime. Okay. So phi defined on the element of this x plus I. Okay. So x plus I, and we have to show phi is homomorphic, so we have to take another element y plus I, phi of x plus I plus y plus I. Okay. So phi of x plus I, y plus I, but x plus I, y plus I is defined in the factor ring is x plus y plus I. Okay. And this one is defined f of x plus y. And phi is defined as x plus I is equal to f of x. So phi of x plus y plus I is equal to f of x plus y, and f of x plus y is equal to fx plus fy. Why? Since this f is homomorphism. So phi x is equal to, what is phi x? Phi x is equal to, fx is equal to phi of x plus I, and fy is equal to phi of y plus I. Okay. Now next one. Phi of x plus I into y plus I. So this is equal to xy plus I. This is fxy. Fx into fy. So fx is equal to phi of x plus I into phi of y plus I. So this phi is homomorphism. This phi is homomorphism. Now, what is R prime? R, let us see. R prime is element of R prime. Okay. We have to show that this is phi is onto homomorphism. This R prime is element of R prime, any arbitrary element. Then what is F? F is onto. So there exists R such that F of R is equal to R prime. Yes, F of R is equal to R prime. But what is F of R? F of R is phi of R plus I by definition. This F of R is equal to this one. Okay. Phi of R plus I is equal to R prime. It means phi is onto homomorphism. Okay, phi is onto. Okay, so phi is isomorphism, and if phi is isomorphism, then R by kernel of f is isomorphic to R prime. Okay. Now see, first isomorphism theorem. What is first isomorphism theorem? If R is ring, and A, B are two ideal of R, such that B is subset of A, B is subset of. Okay. Then the factor ring R by A is isomorphic to factor ring R by B and A by B. Okay. This we have to. For this we will use the fundamental theorem of homomorphism. The fundamental theorem of homomorphism defined in this way: F from R by B to R by A means just like this R and R prime. This one in first fundamental theorem. So this act like R, and this one is R prime. Now define this F of R plus B. What is the element of this one? This is element of R plus B is equal to R plus A. Okay. Define F in this way and prove that this F is onto homomorphism. Prove that this is onto homomorphism. Okay. So if this is onto homomorphism, now how you prove it? This is onto. See, by fundamental theorem. Please wait 1 minute. If we prove it onto homomorphism, then we are done. But how? See, first so it is homomorphism. It is homomorphism, then f of x plus b plus y plus b is equal to f of x plus y plus b is equal to, by definition, x plus y plus a, and this is equal to x plus a plus y plus a, and this one is equal to f of x plus b plus f of y plus b. Okay, so this is the first part. And similarly, f of x plus b into y plus b is equal to f of xy plus b is equal to f of x, is equal to xy plus a is equal to x plus a into y plus a is equal to f of x plus b into f of y plus b. Okay, from first and second, this f is homomorphism. Now this f is onto homomorphism. Okay, similarly we can show that the onto homomorphism. If this f is onto homomorphism, then by definition of first fundamental theorem, this is this f, this r by b is like r and r by a is r prime, then r by kernel of f means r by b kernel of f is isomorphic to r prime, that is r by a. Okay, by fundamental theorem, r prime is isomorphic to r by kernel of f. What is r prime? R by a. What is r? R by b divided by kernel of f. Okay, so what is kernel of f? Kernel of f is, say, r plus b belong to kernel of f. Let r plus b belong to kernel of f. Since the element of r by b is r plus b belong to kernel of f. Then f of r plus b is equal to a. And what is a? A is the identity of this one. Identity of this. What is f of r plus b? F of r plus b is defined as r plus a. F of r plus b is r plus a. R plus a is equal to a. And we know that if a plus h is equal to h, this implies that a belongs to h. It means small r belong to capital A. Small r belong to capital A. It means r plus b belongs to a by b. Right? That is, kernel of f is nothing else but a by b. So replace this kernel of f by a by b. So r by a is isomorphic to r by b divided by a by b. Okay. This is the first isomorphism theorem. Some books are also saying that this is the second isomorphism theorem for ring, and fundamental theorem people are calling first isomorphism theorem of ring, and this one is someone calling second isomorphism theorem, and some books are saying that third isomorphism theorem. Okay, whatever be the first, second or third, right? But we know what is the statement. See, if a and b are any two ideal of ring R, a and b are any two ideal of ring R, then we have to show that a plus b by a is isomorphic to b by a intersection b. Right? And what is this? F of b to a plus b by a. Right? And define it. And define this. F of x is equal to x plus a for all x belong to b. Okay, define in this way. Now this f is well-defined map. This is onto also, you can prove it. Okay. So this F is onto homomorphism. Now apply fundamental theorem. The fundamental theorem says that A plus B by A is isomorphic to B by kernel of F. Okay. What is kernel of F? Kernel of F. Right? Kernel of F, if we are able to prove that kernel of F is equal to A intersection B, then replace this one by A intersection B, then this theorem is, proof of this theorem is done. Okay. But before this, we have to show that kernel of F is A intersection B. Okay. Now what is kernel of F? Let B belongs to kernel of F. Okay. Then say X belong to kernel of F. Then what is Fx? Fx is equal to A. Okay. Since F is in map from B to A plus B by A. So f of x, if x belong to kernel of f, then fx map to identity of this one. What is identity of this factor ring? That is A. Fx is equal to A. But what is fx? Fx is equal to ex plus A. That is A. This implies that ex belongs to A. Right? Ex belong to A. Right? Then ex belong to A. But what is the element of x? What is ex? Ex is element of B. Ex is in A. What is this x? This x is element of B also. So this x is in A and x is in B also. This shows that x belong to A intersection B. It means kernel of f is equal to A intersection B. Okay. Now A plus B by fundamental theorem. A plus B by A is isomorphic to B by A intersection. Okay. Now see the example related to this. So that Z by 2 is isomorphic to this one. See, Z, apply third isomorphism theorem or second isomorphism theorem, whatever you call it. A plus B is by A is isomorphic to A, B by A intersection B. B by A intersection B. Okay, let us see. Let A is equal to 2 and B is equal to 5. Okay, 2 means 2 generated ideal generated by 2 and B means ideal generated by 5. Ideal generated by 2 means 0 plus minus 2 plus minus 4 plus minus 6 dot and so on, and ideal generated by 5 means 0 plus minus 5 plus minus 10 dot and so on. Okay, now what is 10? Ideal generated by 10, that is 0 plus minus 10 plus minus 20 dot and so on, means intersection of these two. Okay, that is 10 is nothing but A intersection B. Okay, and what is 10? 10 is LCM of 2 and 5, that is 10. What is GCD of 2 and 5? GCD of 2 and 5 is 1. So ideal generated by 1 is Z, that is 0 plus minus 1 plus minus 2 dot dot so on. Okay, now A plus B is equal to Z. Okay, so A plus B is equal to ideal generated by 1, that is Z, and A intersection B is ideal generated by 10. Okay, so put all these values here. A is 2, B is 5, A plus B is Z, A intersection B is 10Z. So A plus B is Z, A is 2, right, and B is 5Z. Okay, means ideal generated by 5. You can write it 5 also. Okay, same thing, 5Z or ideal generated by 5, both are same. Ideal generated by 10, that is 10. Okay, so Z by 2 is isomorphic to this one. Now see how to construct factoring. How to construct factoring? Okay. See, if R be a ring and I be an ideal of R, then factoring is defined in this way: A plus I, A belong to R, right? And this is factoring with respect to which operation? R plus and dot. What is plus? Plus is defined in this way, and what is dot? Dot is defined in this way. Okay. With respect to these two operations, R by I with respect to plus and dot is a ring, and we call it factoring. Okay. So construct factoring of Z by 6Z. What is Z by 6Z? Okay. So element of Z by 6Z is element of Z. See here, element of R by I is one element of R plus I. So element of Z plus 6Z. Okay. So consider any element A. Suppose if we consider 1, then 1 plus 6Z. What is 1 plus 6Z? 1 plus 6Z. What is 6? 0 plus minus 6 plus minus 12 dot so on. Okay. So 1, 6 plus 1 is 7, minus 6 plus 1 minus 5, 13 minus 11 dot so on. Right. So 1 plus 6Z. Similarly 2 plus 6Z, 3 plus 6Z, right, dot so on. So Z by 6Z is 0 plus 6Z, 1 plus 6Z, 2 plus 6Z, 5 plus 6Z. And what is 6 plus 6Z? 6 plus 6Z is nothing but 0 plus 6Z. Okay. 7 plus 6Z is nothing but 1 plus 6Z. Okay. So this containing only 6 element. So this isomorphic to Z6 also. Now see, if R is commutative ring, then R by I is also commutative ring. Why? See, XY, A plus I, B plus I. By definition, this is equal to AB plus ABI. But what is AB? AB is element of R. And what is R? R is commutative. So we can write it BA. B plus I is equal to A plus I. And this is YX. XY is equal to YX. It means R by I is also commutative. If R is commutative, then factoring is commutative. Okay. Now construct R by 4Z similar to the R by 6Z. Okay, similar to the R by 6Z. Z by 4Z. That Z by 4Z I think already we explained in our previous lecture also. 0 plus 4Z and 1 plus 4Z, 2 plus 4Z and 3 plus 4Z. And this is nothing but Z4. Okay.